Hello students, welcome back to the maths class. Hello students, welcome back to the maths class. We were discussing chapter 5, that is Euclid's geometry. Let us go ahead with exercise. Okay? Students, let us discuss question number 4. It says that if a point C lies between 2 points A and B such that AC is equal to BC, then prove that AC is equal to half AB. Explain by drawing the figure. Let us draw the figure first. So, as per the question, C lies between 2 points A and B such that AC is equal to BC. Fine. So, this is point A and point B, and suppose this is the point C, so that AC is equal to BC. Fine. That means C divides line segment AB into two equal parts. And to prove, this is your given, and to prove, what we have to prove? AC is equal to half AB. AC is equal to half AB. Fine. So, AC is equal to BC. Okay. AC is equal to BC. I can write that AB is equal to AC plus BC. Fine. So, AB is equal to AC plus BC, because it is given that AC is equal to BC and C divides AB into two equal parts. So, AB is equal to AC plus BC. And as per the given data AC is equal to BC, I can replace BC by AC because C is equal to BC. As we have given data AC is equal to BC, now I can replace BC with AC. So, I will get AB is equal to AC plus AC. That means AB is equal to 2AC, and if I take these two from right hand side to left hand side, it will divide AB by 2. So, AC is equal to half AB. So, in this way we have proved that AC is equal to half AB. Clear? Students, let us discuss question number 5. It says in question number 4, point C is called the midpoint of line segment AB. Prove that every line segment has one and only one midpoint. Okay, let us do it. So, this is line segment AB and C is the midpoint. Okay, that means AC is equal to BC. Okay, so let us assume another point D, and we need to prove that C and D coincide. Okay, we have to prove that C and D coincide. That means there is only one midpoint in a line segment. Okay, so as per the given data, AB is equal to BC. Okay, C is midpoint and D is another midpoint. Okay, that means AD is equal to BD. Okay, this is 1. This is 2. So, if I take AC, that means it is half AB. Again, if I take AD, that is also equal to half AB, because in this case C is the midpoint and in this case D is the midpoint. So, when I combine these two equations, suppose this is equation 3 and this is equation 4. So, when we combine equation 3 and equation 4, I can write AD minus AC is equal to half AB minus half AB. Okay. So, when I subtract equation 3 from equation 4, I get AD minus AC is equal to half AB minus half AB. So, AD minus AC is equal to CD is equal to 0. CD is equal to 0. What does it mean? CD has no length at all. That means C and D, as per this diagram, CD is a line segment. So a line segment should have some amount of length. But we have proved that CD is equal to 0. That means it is not a line segment at all. That means C and D coincide with each other. So point C and point D, they are nothing but coinciding point. That means there is a single midpoint of line segment AB. Hence we have proved that every line segment has one and only one midpoint. Understood? Students, let us discuss question number 6. In figure 5.10, as per your book, if AC is equal to BD, then prove that AB is equal to CD. Let us draw the diagram first. There is a line segment AD. Okay. Two more points are there on line segment AD. One is B, another is C. And it is given that AC is equal to BD. Okay, AC is equal to BD. And we need to prove that AB is equal to CD. Okay, let us prove. As per the given data, AC is equal to BD. So we can write that AC is equal to AB plus BC and BD is equal to BC plus CD. So let us take this as equation 1 and this as equation 2. Okay. So from these two equations, I can write that AB plus BC is equal to BC plus CD. Okay. So as BC is both in the left hand side and right hand side of the equation, I can cancel it out, or I can write that AB is equal to BC plus CD minus BC. So when I cancel this out, I get AB is equal to CD. So hence proved. We need to prove that AB is equal to CD. So we have proved that AB is equal to CD. Hope you understood. Students, let us now discuss question number 7. It says, why is axiom 5 in the list of Euclid's axioms considered a universal truth? Okay. What the axiom 5 says? The axiom 5 says that whole is always greater than a part. Whole is always greater than a part. Let's draw a diagram and discuss it. Suppose this is a line segment AB. So in this case, AB is a line segment which can be treated as a whole. Let us have a point C over here on the line segment AB. So it is clearly obvious, or it is obvious that AC is less than AB. What is AC? AC is nothing but a part of the whole, isn't it? So AC is a part of the whole. That means AC is a part of AB, and it is obvious from the diagram that AC is less than AB, or I can say AB is greater than AC. So it is a universal truth that a whole is always greater than a part. Hope you understood. Okay. So students, we have completed exercise 5.1. Now let us discuss some more concepts about Euclid's geometry. equivalent versions of Euclid's fifth postulate. Euclid's fifth postulate is very significant in the history of mathematics. Recall it again from section 5.2. We see that by implication no intersection of lines will take place when the sum of the measures of the interior angles on the same side of the falling line is exactly 180 degree. That means two lines, they go parallel to each other. There are several equivalent versions of the postulate. One of them is Playfair's axiom, okay, which is given by a Scottish mathematician John Playfair in 1729. It states that for every line L and for every point P not lying on L, there exists a unique line M passing through P and parallel to L. As you can see in the diagram given in your book that all the lines passing through the point P, there is a line M which is parallel to L because that line is passing through P and it is unique. All other lines, those are passing through point P, which are the dotted lines, okay. They are intersecting line M, but the only line M is parallel to L. Why? Because both line L and M, they are equidistant from each other throughout. So students, Euclid did not require his fifth postulate to prove his first 28 theorems. Many mathematicians, including him, were convinced that the fifth postulate is actually a theorem that can be proved using just the first four postulates and other axioms. However, all attempts to prove the fifth postulate as a theorem have failed. But these efforts have led to a great achievement, the creation of several other geometries. These geometries are quite different from Euclidean geometry. They are called non-Euclidean geometries. Their creation is considered a landmark in the history of thought because till then everyone had believed that Euclid's was the only geometry and the world itself was Euclidean. Now the geometry of the universe we live in has been shown to be non-Euclidean geometry. In fact, it is called spherical geometry. In spherical geometry, lines are not straight. They are parts of great circles. Okay? Circles obtained by the intersection of a sphere and planes passing through the center of the sphere. As given in your book, in figure 5.12, the lines AN and BN, which are parts of great circles of a sphere, are perpendicular to the same line AB, but they are meeting each other, though the sum of the angles on the same side of the line AB is not less than two right angles. In fact, it is 90 degree plus 90 degree, that is equal to 180 degree. Also, note that the sum of the angles of the triangle NAB is greater than 180 degree, as angle A plus angle B is equal to 180 degree. Thus, Euclidean geometry is valid only for the figures in the plane. On the curved surface, it fails. Now, let us consider an example. Students, let us discuss example 3. Consider the following statement. There exists a pair of straight lines that are everywhere equidistant from one another. Is this statement a direct consequence of Euclid's fifth postulate? Explain. So, take any line L and a point P not on L. Let us draw it. This is suppose line L, okay, and a point P not on L. Suppose there is a point P over here which is not on L. This is line L, okay. Then by Playfair's axiom, which is equivalent to the fifth postulate, we know that there is a unique line M through P which is parallel to L. That means if I draw a line M which goes through P, it is a unique line. This only line is parallel to L. As we have discussed previously, there might be many more lines which can go through P. We can draw many lines, or we can say we can draw infinite number of lines. We have discussed before that infinite number of lines can pass through the single point. So these are suppose the lines, but the unique line, the line M, it is unique because it is parallel to line L, and I can say M is parallel to L. Okay. Now the distance of a point from a line is the length of the perpendicular from the point to the line. This distance will be the same for any point on M from L and any point of L from M. So these two lines are everywhere equidistant from one another. That means if there is a point, suppose this is A on L, and if I draw a perpendicular line which intersects line M at point B, and if AB is perpendicular to L, this distance is constant throughout. If it is constant throughout, for any point on M, if I draw a perpendicular on L, okay, suppose this is point C, and if I draw a perpendicular which intersects L at D, that means CD is perpendicular to L, okay, CD is perpendicular to L, this distance, that means CD is equal to AB. CD is equal to AB. In that case, in which case? In the case L is parallel to M, or you can say M is parallel to L. All the perpendicular distances between 2 points which lie on M and L are equal. So the perpendicular lines, or the distance between a point and another point between two different lines, okay, in this case M and L, that remains constant. Okay. So the geometry that you will be studying in the next few chapters is Euclidean geometry. However, the axioms and theorems used by us may be different from those of Euclid's. Okay. Students, let us recall postulate 5. What it says? It says if a straight line falling on two straight lines makes the interior angles on the same side of it taken together less than two right angles, then the two straight lines, if produced indefinitely, meet on that side on which the sum of angles is less than two right angles. Isn't it a bit critical? Let's simplify it. Okay. Let us discuss what it says again, so that we can come to another statement which is same as postulate 5. Okay. Students, as you can see, I have drawn 3 different lines. Let's name it L, M and N. So M and N are 2 different lines, and L is passing through it, intersecting the 2 lines at suppose point P and Q. Okay. So thereby constructing 4 internal angles these two are two internal angles and these two are other internal angles. So, we have two pairs of internal angles. So, when as per the postulate, we can clearly see that the sum of these two angles, this angle and this angle, suppose this is angle A and this is angle B. Let us write it over here. This is A, this is B. A and B, we have already proved while discussing postulate 5 that angle A plus angle B is greater than 180 degree. And if I write it as angle C and angle D, we have already proved that angle C plus angle D is less than 180 degree. So, as per the postulate 5, when we produce the lines in the direction or in the side of the internal angles whose sum are less than 180 degree, then both the lines will meet at some point. Okay. So, when I produce line M in this direction and line N in this direction, because in this direction the sum of the internal angles is less than 180 degree. So, they are meeting at certain point or they are intersecting each other at certain point. Okay. So, I can say that if I simplify, I can say two lines while intersected by another line, okay, two lines, or I can say two distinct lines while being intersected by another line will meet each other at another point in the direction of the alternate angles whose sum are less than 180 degree. Okay. Again I am repeating, I can say two distinct lines when they are intersected by another lines will intersect each other at another point in the direction of internal angles whose sum are less than 180 degree. Okay, you can note it. I repeat it again, two distinct lines when intersected by another line will meet with each other at a point which is in the side of the internal angles whose sum is less than 180 degree. Okay, hope you understood this. Students, let us discuss question number 2. It says, does Euclid's fifth postulate imply the existence of parallel lines? Explain. So, let us discuss. What we come to know from Euclid's fifth postulate, that two lines while intersected by another line will meet, okay, they will meet at certain point in the side in which the internal angles or the sum of the internal angles is less than 180 degree. So, let us draw another diagram. In this diagram, I have drawn three straight lines. Let us name these as L, M and N. Again, if I go to postulate 5, these two lines will meet each other in the side where the sum of internal angles is less than 180 degree. But a point will definitely arise in which the internal angles in one side, let us first draw or name the internal angles as A, B and C, D. So, internal angles in one side of the intersecting line are A and C towards left and B and D towards right. Okay. So, there is a point in which the sum of the internal angles in one side of the intersecting line, which are also called as co-interior angles, which we have already studied in previous chapters. Okay. So, AC are also called co-interior angles. So, a point may be there where A plus C is equal to 180 degree. That means B plus D is equal to 180 degree. As per the postulate, if the sum is less than 180 degree, the lines will meet with each other, isn't it? Postulate says if the sum of the internal angles one side is less than 180 degree, then they will meet with each other. But in such cases where the sum of the internal angles one side of the intersecting line is equal to 180 degree, they will never meet, because postulate 5 says that they will meet with each other when the sum is less than 180 degree. So, when it is 180 degree, they will never meet. And what we know, that the parallel lines, they never meet with each other. That means they maintain equal distance between themselves. So, in this case, M is parallel to N. They are not going to meet with each other on either side of the intersecting line L. So, we can say that Euclid's fifth postulate imply the existence of parallel lines. Clear? So, dear students, with this I am going to conclude this chapter. Before that, let us discuss the summary again. In this chapter, we have studied the following points. Though Euclid defined a point, a line and a plane, the definitions are not accepted by mathematicians. Therefore, these terms are now taken as undefined. Second, axioms or postulates are the assumptions which are obvious universal truths. They are not proved. Third, theorems are statements which are proved using definitions, axioms, previously proved statements and deductive reasoning. Fourth, some of Euclid's axioms were things which are equal to the same thing are equal to one another. If equals are added to equals, the whole are equal. If equals are subtracted from equals, the remainders are equal. Things which coincide with one another are equal to one another. The whole is greater than the part. Things which are double of the same things are equal to one another. 7. Things which are halves of the same things are equal to one another. Then we have discussed Euclid's postulates, which were postulate 1, a straight line may be drawn from any one point to any other point. Postulate 2, a terminated line can be produced indefinitely. Postulate 3, a circle can be drawn with any center and any radius. Postulate 4, all right angles are equal to one another. Postulate 5, if a straight line falling on two straight lines make the interior angles on the same side of it taken together less than two right angles, then the two straight lines, if produced indefinitely, meet on that side on which the sum of angles is less than two right angles. Summary 6. Two equivalent versions of Euclid's fifth postulates are: first, for every line L and for every point P not lying on L, there exists a unit line M passing through P and parallel to L. Second, two distinct intersecting lines cannot be parallel to the same line. Summary 7. All the attempts to prove Euclid's fifth postulate using the first four postulates failed, but they led to the discovery of several other geometries called non-Euclidean geometries. Okay. So, with this we come to the conclusion of this session. You revise everything that is taught to you, keep practicing and keep smiling. stay healthy, stay safe. Okay? Thank you.